Okay, let us now discuss about the simulation of this flywheel experiment. So, basically a flywheel is a large wheel, a bulky wheel, heavier bars, and it is moving along this axle. So, what actually happens is the arrangement is that you have a thread attached to a weight. It is touching this ground here at a particular height. So, at this height, the energy possessed by this is potential. And when you rotate this wheel, when you are rotating this wheel, what happens? It is acquiring the kinetic energy. That energy is transferred to the axle and it will acquire and starts rotating. After some time, this thread which is wound on this gets detached from the flywheel, touches the ground, and then flywheel, because of the air resistance and other frictional forces which is being present, comes to a stop. So there is always a conversion of energy from kinetic to potential, and this flywheel acts as a storage device which is transferring the energy from one form to the other. So the experiment here involves, you can choose, these are the variables here, you can choose different planets, Earth, Moon, Uranus, Saturn and Jupiter. Okay. And then other variables are, you can vary the mass. You see, as you can change this, you can see the mass is changing. You can go up to 5.5, 50 kgs. It's becoming heavier and heavier. So fix it at a particular constant value, and then diameter of the flywheel can also be changed. As you see, it is changed. So fix this also at a particular point. Then diameter of the axle. Axle is this rod that he is referring to, and that can be changed. As you see, as the diameter is increased, it is this axle. Diameter of the axle is this. So it is this which is changed. Now what you do is, you fix the mass, you fix the diameter also at a particular constant value, and then diameter of the axle also you keep it fixed. You change the number of windings, the thread windings, let us say 1, 2, 3, 4, let's say 5, fix it at 5. You can count the number of threads here, they are equivalent to 5. And then you can change, keep these things fixed. You can repeat this experiment for different masses. 200. See, each weight hanger is 200. So when you add 2, it becomes 400. Then this is 600. 800. This is 1000. So fix it at a particular value and then release the flywheel. You have to do, release the flywheel. What's happening? It started slowly unwinding itself. You can see the number of cards are getting 5, became 4, 3, 2, 1, and it's touching the ground. It's getting detached from the flywheel. That is when, wait till the flywheel comes to a stop. Slowly it is moving now, it's unwinding. A stage comes where it becomes almost a zero motion, or it comes to a stop. Yeah. So 11 seconds it is taking for it to come to stop, and here find the result. That will give you the moment of inertia of the flywheel, which is 0.1433. Okay. So now what will you do? You go to so what have you taken? Mass is 200. Whatever values of flywheel, mass, diameter and so on. Make a note of all this. Go to the data sheet and enter the values here. Let us see. where will you enter these values? So prepare your Excel sheet before you start your experiment. And in that Excel sheet, this sheet should have been kept ready. So mass of the flywheel, is 5 kgs, diameter of the flywheel is 20, diameter of the axle is 3. Fix these. Okay, once you fix this, now you perform the experiment. I think you performed it on which planet? We performed it on the Earth. So come here and then on Earth. So 5. Number of chords is 5. Fix these values. Your mass, diameter of the axle, you fix it. And on the planet of Earth, you change the mass from 200, 400, 600 and 1000. Repeat this experiment for 5 bounds, 6 bounds, 7 bounds. Likewise, you can choose different environments: Moon, Uranus, Saturn. I think one more is there. Yeah, Earth, Moon, Uranus and Saturn. Find out these values. And then find the value will be calculated. You already calculated, you get the value here as 0.1433. You can repeat this experiment for, let us say, a reset. You must reset it and then increase it to 400. Release flywheel, find out the time and then show the result. It will show you the result, 0.0063. So likewise, you calculate repeat this for all the different planets and different weights. Find the for 5 windings, 6 windings and 7 windings. This set, so different sets for different planets. Then mass is varied from 200 to 1000. Calculate and find out the result. So this is one experiment you have to do using flywheel. Another experiment similar to this is, aim is the same in both the cases. You are finding the moment of inertia only. The aim remains to find the moment of inertia. Aim of the apparate simulation is to calculate and compare the experimental and theoretical moment of inertia by varying the radius of the disk types, flywheel and mass of the metal one. So in this experiment you are varying the radius and the mass. You are doing it only on one planet, which is Earth. In the previous experiment you are changing the mass also, radius and other things are kept constant. So now let me show you the simulation. So this is the apparatus, as you can see. You can vary the radius and the mass. So initially this is the mass. N1 are number of oscillations is that windings which you have seen in the other experiment. You are not able to see that, but this will give you the number of revolutions that is made, and then this is the time it takes, and then this is the radius. So what you have to do here, it is at a height here. Again same concept. The kinetic energy is translated to the potential energy. At this height, it possesses mgh, the potential energy. So first, release the control here. See, you can see. The ball is slowly going down. It touches the ground. The moment it touches the ground, it's touched the ground now, which is at a height of 2 meters, is touching the ground. Now, the flywheel slowly moves back, unwinds itself, it's unwinding. After a certain time, slowly, you can see that the wheel is now getting slowed down, slowly. has come to a stop now. So you are expected to calculate the moment of inertia theoretically using the formula mr square by 2. Experimentally another formula is there. Calculate and submit. Okay. Now what all are required for calculation of this moment of inertia using the formula? You need angular velocity and number of oscillations it takes for the flywheel, the number of oscillations it completes after the mass touches the ground. It revolves so many times before it comes to stop. So these are the number of revolutions made after the mass is released from the axle, and this is the time taken. So now how do you calculate? To calculate this, let's now see our data sheet. Let me go back to my Excel sheet. This is to determine the moment of inertia of a flywheel. Also your determination of moment of inertia of a flywheel, and compare the theoretical and experimental values. This is your aim of the experiment. So now what all are you varying here? You are varying the radius, mass of the wheel. So radius you do only 10, 15 and 20, 3 readings, and vary the mass from 0.2, 0.4, 0.6 and 0.8 up to 1 kg. Theoretically I showed you the formula is mr square by 2. M is mass, which is there already written, r radius also is given. Perform this calculation. And then moment of inertia using the formula is given by m into 2gh by omega square minus r square divided by 1 plus n1 by n2, where let us see what these are. M is mass which is attached, g is acceleration due to gravity, h is height, v is velocity, that is also given in the table, omega is the angular velocity, and then this is the number of rotations completed by the flywheel is n1. This is number of rotations made by the flywheel after the string has left the string of the axle is n2. So now let's go back to your experiment. So you perform this experiment just now. So you need n2, you need omega, you need n2, you need omega. These two you have taken, and then mass is this. So m, what is the radius? Radius is 0.01898 meters. So m r square by 2. So 37.81. So what will you write here? Here, how do you calculate? Just go down, calculate. This m is small m. Mass of the wheel, what you have? Mass of the, this is not mass of the wheel, mass attached to the wheel. This is a mass attached to the wheel. So that you have to calculate in each case, and this will be common because you are not changing the radius. So this is, let me choose this some cell, is equal to, what is your m? M says, m is 37.81. So 37.81 37.81 m, and then into r square. So put a bracket. R, what is R? How much is the value of R? Value 0.01898 meters. 0.01898. 0.0198 into 0.000198 r square divided by 2. So this is how you will be calculating, and verify this using the theoretical and observational values. So this is how you will be doing this. So these are the two experiments. Both are calculating the moment of inertia in two different ways. Tabulate the results in the Excel sheet